Hello all, welcome to this course on time series modeling and forecasting using R. Okay. So, we are almost done with week 11 here, and then after week 11 there will be one last week which will be left, and this would be a practical session within week 11. Now again, just to give you again, as always, my habit is just to sort of start with a very quick refresher, right, so that people do not seem to be disconnected with what has been done in the theory. So, throughout this week we studied the idea about non-linear time series processes. So, we started the regimes, different kinds of regimes, then specific kind of models, let us say TAR model or star model, SE TAR model, right. And the last session we talked about the third kind of a regime, which is called as Markov switching models, right. So, I think now is the time to sort of connect all the theory and then get our hands dirty using some, let us say, simulated data or real data. So, we will try to sort of implement all the models we have seen this week on some set of simulated data or rather real data across multiple areas, etc. Okay. Okay. So, again, get your laptops open and then get your R worksheets running, and then by the way, this worksheet kind of requires all these packages, right. So, since non-linearity is not very much easy to understand, so the first thing to do is to install all these packages. Okay. So, let us say TSA and then forecast and then quant mod, then TSDYN, stats, dsolve, T series chaos, etc. Okay. So, again the very first step would be to go into tools and rather click on install packages and then try to install each and every package here. Okay. And again, of course, once you have installed all the packages, do not forget to call them in the R environment also using a library command. Okay. So, let me quickly do this for each and every package here. So, TSA forecast, quant mod, TS dyn, stats, dsolve, T series chaos, etc. Okay. And now, once you have made sure that all the packages are there which are required, then you can start running the codes. Okay. So, now the first thing is, as always, set.seed 1 2 3. Again, if you want to regenerate the code, then R would start from the same point, but ensure some randomness. Okay. And here again, as always, you can give any random number that you want. So, we will give 1 2 3 for the time being. So, set.seed and then 1 2 3 here. Okay. So, now the very first part of this code would be running some examples on simulated data. So, part 1 would be focusing on simulated data example, and simulating which model exactly? So, simulating a self-exciting threshold AR process or rather SE TAR model. Okay. So, self-exciting TAR model or rather self-exciting threshold AR process, or in short SE TAR process. So, the very first exercise we will do is, depending upon some fixed parameter values, we will try to simulate from a SE TAR process. Okay. So, for that we will fix the sample size first. So, let us say n is 500 and then all the parameters we have to fix. So, let us say threshold value. So, it will specify some threshold value. So, being a threshold kind of a model, you would always specify some threshold value. So, let us say we will keep the threshold value to be 0 for the time being, and then we can define all the parameters. So, phi 1 is the AR coefficient for regime 1, phi 2 is the AR coefficient for regime 2. So, my phi 1 happens to be 0.8, my phi 2 happens to be minus 0.5, and sigma is nothing but the standard deviation of the error term or the noise term, which is assumed to be 1. So, once you fix all the parameters, then you can sort of go ahead and simulate from that SE TAR model. Okay. Now, beforehand I will do one small exercise, is that y and then arrow numeric n. So, I am considering that the value that my y is taking, okay, is nothing but the value that my n is taking initially. Okay. And now, so this is a small loop kind of a structure where I am generating the SE TAR process. Now, again remember one thing, that in SE TAR you have two regimes, right. So, depending on one threshold value, so given one threshold value, it splits into two regimes, and within each regime I am trying to fix some AR model. Okay. So, again just to very quickly explain what is going on in this chunk of the loop that you see here, that let us say t going from 2 to n. So, t is a pointer or rather a counter. So, t going from 2 to n, if my last value of the time series, so y t minus 1 is less than equal to the threshold, it will be in the first regime, right, else it will be in the second regime, and this is exactly as per the SE TAR definition. So, again if you sort of vaguely remember the model structure we have seen in last couple of sessions about the SE TAR process, then this is exactly what happens there, right. So, you look at the threshold value And again the threshold value here is nothing but the past value of the time series itself. So, y t minus 1. So, if that threshold value is less than or equal to the fixed threshold value, which is 0 in this case, then the time series would be in the regime 1, or otherwise else means that y t minus 1 exceeds the threshold or exceeds 0, then you will switch to regime 2. Make sense? And within each regime what model you have? So, within each regime I have a AR structure or simple AR structure. Make sense? So, let me run this loop. So, again generating the SETAR process should not be difficult, and again understanding what goes inside the code or what goes inside the loop should not be difficult now. Okay. So, let me run this overall for loop, and now let me show you the plot. So, the first plot would be the plot of the simulated SETAR process, which looks something like that. Okay. So, let me zoom in. So, this is exactly how the simulated SETAR process looks like. So, again this process is not a whole lot different from any of the other simulated process we have seen, let us say in the last practical session or the one before that, etc. So, one can't basically or rather differentiate a simulated SETAR process from, let us say, any of the other AR processes, right. At the end of the day, it is a simulated process. So, one key characteristic could be that there could be some hidden non-linearities in the underlying data. Okay. Alright, so this would be a simulated SETAR process, and then I'll include an AB line on the threshold value just to sort of specify or rather focus on the threshold variable, which is 0 here. Okay. So, the horizontal red line that you see is in fact on 0, which tells you the threshold value in the underlying SETAR process. Okay. So, let me close the graph. And now the second kind of model we will try to simulate is a TAR model. So, the SETAR model is done, and then the second model we will try to fit would be a TAR model or a threshold autoregressive model to the simulated data. Okay. So, again what we will do is we will again pick up the same vector y, right, and then we will give it a slightly different name, let us say TAR underscore model underscore sim, and then you have this inbuilt function in R in one of the packages we loaded earlier, is called as TAR. So, TAR, and this is nothing but the syntax part. So, what goes inside the TAR function is nothing but you specify the time series value, which is y, and then alongside you specify P1 equals 1, P2 equals 1, D equals 1, and A is the threshold. Okay. So, now let me run this, and then I will show you a quick summary of the fitted TAR model. So, this is the summary of the TAR model, and this is rather the fixed, all the fixed parameter values we have taken. So, P1, Q1, D, QR1, QR2, etc., and the overall length. Okay. Alright, and then the key part is once you fit any of the models, you have to always check for the residuals, right. So, I can do that by plotting the residual diagnostics, and then this check residuals command in R is kind of very helpful to do that. Now, we will be checking the diagnostics for which model? Again the TAR model. So, check residuals applied on the TAR underscore model underscore sim. Okay. So, once you run this, then it will give you 3 kinds of different plots. Let me again zoom in, and these are the key assumptions that we are making, right. So, if you are kind of into time series modeling, let us say be it ARIMA or be it TAR, be it STAR, be it SETAR, whichever model, but again once you are through with the model building, you have to always ensure that the residuals follow normality. So, which would be given by the histogram. So, here you can clearly see that the residuals are indeed following a symmetric bell shaped curve, which might resemble a normal distribution. Now, of course, on top of that you can do all sorts of hypothetical tests, let us say Shapiro-Wilk or Jark-Berra, some sort of a formal test to sort of confirm the normality, but again if a histogram is looking as solid as that, then probably you need not even go for some of the hypothetical tests. Okay. On the other hand, this is nothing but the distribution or a raw plot of the residuals, and here you can see that the residuals are sort of, they do not have any inbuilt pattern in them. So, they are completely random, and variance is not an issue here. So, variance would be assumed to be constant, right, which can also be seen using the ACF plot. So, the ACF plot you can see that almost all the spikes are within the bounds, which is a clear indication that all the assumptions about the residuals are met here. Make sense? So, here again one small point is that if you see any discrepancy or some disconnect in any of the plots, let us say normality or changing variance or autocorrelation, then again you have to again go back, you have to push back a step and then again try to, let us say, propose a slightly different model, then fit that model, check for the residual. So, you have to do some back and forth kind of an exercise. Okay. But once you are ensured that all the assumptions are being met, which they are in this case, then you can go ahead with the forecasting. Okay. Alright, so I will close the residual plots. And now the last thing is forecast with the tar model. So, and then we'll give it a name, let's say sim underscore forecast, and then again predict is an inbuilt function, and we've used this predict function even multiple times before. And predicting which model? So, we want to predict the tar model, and how many time steps ahead? So, let's say 20 time steps ahead. So, let me run the forecast and let me give you the plot. Okay, so plot and then along with the lines. All right. So, let me close this first. Let me recreate the plot. All right, and then I'll click this as yes. By the way, I'll show you one trick. So, as of now, within the plotting window, you must have seen that R is giving you multiple plots in the same window, right? So, how do you correct that? So, let me scroll down. I think I have the code here somewhere for that. Or rather if not, yeah, for example here. So, you have to run this line, so that you see in line 101. So, this would again go back to having one plot in a single window, right? Because again, let us say that if you do not want, let us say, multiple plots in the same window, then why would you want smaller plots, right? Okay. So, again I do not want to have all the individual plots in a small font. So, again you might want to run this. So, this tells R that I only want one plot per row. Okay. So, PAR and then MF row equals concatenate 1 comma 1. So, let me run this. Okay, and once you run this, and if R is not throwing any error, then you are good to go. So, again you scroll up to the forecast plot. This is exactly what we were doing. So, again let me rerun just in case the forecast code and then the plot. Okay, so now I think this is much better. So, this is the actual plot of the simulated data, and this is the forecasted. So, let me zoom in just to sort of tell you exactly as to how the forecasts are looking like. Okay, so again this is the simulated data up to this point, up to 500, and the blue dots that you see are nothing but the forecasted values using the tar model, okay, or rather the tar model forecasts. Alright, so again let me go back to the code. Now, once we are through with the simulated data, we will get our hands dirty with exploring using some real data. Okay, so the part 2 in this code would be real data example, taking the example of the Nile river data. So, for that we will load the Nile data set first. So, let us say you load the Nile data set first using data, and then you specify the Nile as a name. Okay. And again, just to quickly show you as to what this Nile data set contains. So, again I can run question mark on Nile, and it should give you a small description on the right hand side. So, this Nile data set gives you the flow of the river Nile. So, measurements of the annual flow of the river Nile at a particular location called as Aswan, and over all these years. So, 1871 to 1970 in, let us say, these units with apparent change point near 1898. So, this is such a data, the Nile data, that if you talk about the flow of the river Nile, it has a very strong change point in the year 1898. Okay, and then I'll show you the plot, don't worry, but then the change point kind of points to a fact that probably a linear kind of a time series structure may not be good here, right? Because if the time series or the behavior is changing, you have a strong change point somewhere in between, then probably this indicates that you have a threshold value and then you have some regimes, okay, and the time series is transitioning between these regimes. Okay. Okay, so again going back to the data, which is Nile, and then let us say I will give it a name to extract only the flow data. So, I will give it a name as Nile underscore flow, which is nothing but as.numeric applied on Nile, and then exploring the data. So, let us say summary variables, some preliminary summary variables of the Nile flow data. So, these are the values. So, let us say the mean flow is 919, of course, in those units that you see on the right hand side. This is the minimum flow, this is the maximum flow, so 1370, how much is Q1, how much is Q3, how much is Q2, etc. Okay. And here I will just quickly show you the histogram of the underlying data. So, the Nile flow data looks like that. So, let me zoom in one more time. Okay. So, here clearly you can see that majority of the flow values lie between, let us say, 600 to 1200 roughly, or rather 1300, right, and then these two could be outliers here. Okay. So, one on the lower end and then the other one on the upper end. So, this is a broad histogram about the flow data, which is the Nile flow data. Alright, so now once we are through with sort of understanding a few ideas from the histogram, then we can start sort of putting forward some models on the data. Okay, so the very first model we will try is checking for the SE-tar against linearity. Now, here what we will do is, let us say if you assume linear model and then you assume that linearity is not good enough then you want to put forward some non-linear model, then how do you check for a SE-TAR model against a linear model using some hypothetical test. Okay. So, this SE-TAR test, which is an inbuilt function in R, exactly does that. So, how exactly? So, I will show you. So, SE-TAR test applied on the Nile flow data, m equals 3, n boot equals 400. This is part of the syntax. Let me run this, and then probably will take a short while to run, because the SE-TAR test sort of takes into account all the iterations in the background and then throws you the best possible models. Okay. So, please give it half a minute to run, do not panic. So, in some situations, if you see a stop sign here, then now it is done, of course, but if you see a stop sign here, then you see that a program is running. Okay. So, if a program is running, you should not do any other codes there, and then you should stop once the stop sign has gone, basically. Okay. All right. Anyway, so this is a test of linearity against two models. So, SE-TAR 2 and then SE-TAR 3. And how do you read this is that if you read, so the first row gives you 1 versus 2. So, linearity against SE-TAR 2, and then second it gives you linearity against SE-TAR 3, and it gives you the corresponding p values. Of course, it gives you the test statistic values, but we are not concerned about the test statistic values, but more about the p values. So, in the first row, if you see, the p value is slightly significant, of course not at the 0.05 level, but let us say the 0.1 level. So, if you fix alpha to be 0.1, this could be significant. Of course, this is not significant. Okay. So, what it means is that SE-TAR 2 model could be slightly preferred as compared to linearity, but of course, SE-TAR 3 model might be overfitting. So, SE-TAR 3 model is not preferred, because if you see here, p value is not less than 0.05 or 0.1, right. But since this p value is less than 0.1, we can sort of conclude that SE-TAR 2 model might be preferred as compared to a linear structure. So, hopefully, the idea of the SE-TAR test is clear, that SE-TAR test, again just to summarize, gives you a sort of a comparison between linearity and any of the non-linear models. So, in this case SE-TAR model. Okay. Now, how do you select the SE-TAR model, right? So, once you make sure that there could be a possibility of putting forward some sort of an SE-TAR model on the Nile flow data, then how do you select the orders? Okay. So, I have run this line 61, again probably just wait for less than half a minute, and then this throws you this table, and probably the first attention point of view from in your situation should be the last column. So, last column gives you the pooled AIC value, and basically you have to scroll down the line and then basically find out the model which has the least AIC, of course. Okay. And out of all these 10 different iterations, probably the very first model corresponds to the least AIC, which is 1238051, and then you sort of trace back in that the first row, and then these are the parameter values. So, the threshold value is 912, by the way. Okay. So, corresponding to the first model, the threshold value is 912, the other parameter, the delay parameter is 2, etc. But once you are sure that which level or rather which row to focus on, then again you can create the model now. So, how do you create the SE-TAR model on top of the Nile flow data? You can use again the same function called as SE-TAR, but applied on the Nile flow data. But here you fix some of the parameters which you get from this table, by the way. So, how much is the delay? So, delay is 2. How much is the threshold? So, threshold is 912, etc. Okay. So, once you run this, then you can run the summary of the model, and then this is exactly the model that you have along with all the estimated parameters. So, phi L1, phi L2, phi L3. By the way, here you can clearly see that you have two regimes. So, one is a low regime, and this is usually the syntax that R follows. So, L stands for low regime, H stands for high regime, and within each regime I have a AR structure containing 3 coefficients. So, phi 1, phi 2, phi 3 in L, and similarly phi 1, phi 2, phi 3 in H. Make sense? So, this is exactly what R throws at you. So, estimated coefficients, this is the threshold variable which takes that form, threshold value is 912, etc. Okay. So, now at this point we have successfully tried to model the Nile flow data using a SETAR kind of a model, and then the forecast, right. So, one can always forecast it down the line, and then using again the predict function, and how many time points down the line. So, let us say 10 time points down the line. So, n dot ahead is 10, and then if you want to output the values, I can always write down Nile underscore forecast. So, all these are the forecasted values, or rather the forecasted flow values down the line. Make sense so far? Okay. So, now another data set. So, let us say enough about Nile data set. So, let us say there is one more very famous data set which people analyze, is called as sunspots data. So, firstly, what exactly are sunspots? So, sunspots are nothing but small black spots on the surface of the sun, and then these are sort of capable, or rather very helpful in understanding the different wave mechanisms. So, let us say electromagnetic waves, right, all these kind of ideas. So, sunspots data is, so a lot of physicians kind of use this data to analyze multiple things. Okay. So, again here we will make use of the sunspots data. So, I will show you the plot of the data first. So, plot.ts of sunspot.year, and then this is exactly how the sunspots data looks like. Let me zoom in. Okay, and then here you can clearly see that there might be a very slight trend, slightly upward trend, but again you can see some seasonality, or rather some cyclicality here. Okay, so again these are some of the features that one should always keep in mind when you see any of the time series plot there. Okay, all right. So now test for linearity. So again we haven't discussed these in the theory, but I thought that I'll just throw these two tests in the practical session. So these are some hypothetical tests. Again, don't go into details as to what is a test statistic, etc. But the names are Keenan test and then TSAY, so psi test. Okay, so Keenan test and then psi test applied on sunspot year. And then what would these two tests give you is that if you run these two tests, then of course it will throw you a p-value. So again for the Keenan test, the p-value is pretty small. Again for the psi test, the p-value is pretty small. 6.6 into 10 to the power minus 12, which means that you can actually reject the null hypothesis of linearity. So, since you are testing for linearity, my H naught or my null hypothesis is that the model is linear, which you are sort of rejecting here, because the p value is very small. Make sense? So, in fact, both these tests are pointing to the same idea or same notion that the underlying time series model need not be linear, and it is a good idea to explore for some non-linear structures. Now, what exactly is this? So, we will try to fit some model here, right. So, we will try to fit some model using this AICM technique. So, again I am pretty sure that we have not discussed this in the theory, but this AICM technique, what it does is, it sort of, again you can see a for loop going from 1 to 9. So, it takes each and every iteration and then gives you the best possible model. Okay. So, I will run this for loop and then column names, row names, and then AICM table. So, this is exactly what the AICM table looks like. Again kind of a similar looking table as we saw earlier. The column to note here is the AIC column, and then one should identify the minimum AIC as much as possible. And here if you scroll down, I think the minimum AIC is nothing but given by the 9th row, right, which is 2221. So, in between we had a slightly lower AIC here, which is 2226, but 2221 is of course the least AIC. So, one should go with that. Okay. And once you identify the model, then you have to read the 9th row to identify the other orders. So, what is R, what's P1, what's P2, etc. Okay. And then lastly we will be fitting the model containing all these values on the sunspot data. Okay. So, P is 9, D is 9, A is 0.15, B is 0.85, etc. And then this is done. And then now once you fix the parameter values, now we can fit some sort of a tar model on that data. Okay. So, sunspot.tar.best would be fitting a tar model on the sunspot data, and all these parameter values are from the table that we saw just now. So, let me run this, then let me run the plot. Now again as you see that you see some error in plot.new, that figure margins are too large, right. And probably you have covered this some of the earlier practical sessions as well, that if R throws an error like this, you have to basically run this line. So, par MAR equals 1111. So, if you run this and then again go back and try running the tsdig command, okay, now again I think it is throwing you the same error, but again, so idea is that it should throw you. So, I think this line should sort of get rid of the error, which is not happening here. That is okay, but ideally that should happen. So, this tsdig should output some plots, some visual plots. Okay. Okay. Anyways, let us go for prediction, forecasting, etc. So, let us say you can forecast down the lines using the sunspot data, and then how many time points down the line. So, let us say 10, and then if you want to extract the predicted values, so sunspot.pred, then you can have a plot. Again it is saying figure margins are too large. Let me try to run this one more time, okay, and let us see if this happens now. Yeah. So, now we have the base plot and then we have the added line. So, this is the sunspot data, this is the forecasting window. this is the upper limit, this is the lower limit. Okay. Now, let me zoom in. Again here if you see that R is again giving one small plot rather than one single plot in one window. So, how do you counter that? So, I can again run this line and let me again go back to creating all these plots one by one. So, plot of the predicted values, then the lines, then the actual forecast along with the interval. Now, let me zoom in and now this would give you a better picture. Okay. So, this is the actual sunspots data along with the TAR forecasts. So, the dotted or rather the dashed line gives you the TAR forecasts. Okay. And again probably I will skip this last bit because the time is not there, but again as a small disclaimer given the last practical session as well, that a strong suggestion would be to again go ahead and then try to complete this entire worksheet from your end. And then by the way, this one piece which is sort of remaining is fitting some linear AR model, and then how do you identify the order of the AR model. So, all those things. Okay. But since this is not very much related to, let us say, non-linearity, so probably it can also be best if you skip it basically, right. So, think that the code has ended here up to line 101 because we have kind of fitted two different models, right. So, TAR model and then SE-TAR model, and then we have seen that we fitted on two different data sets. So, the Nile flow, sunspots, we have forecasted down the line, we have compared, etc. So, I think this would be a strong understanding about the entire idea about non-linearity. And now we are entering into week 12 from of course the next session, and then the idea there would be to explore the ideas about machine learning integration, or rather let us say deep learning integration with time series. So, applications of time series connecting with machine learning or deep learning, reinforcement learning, neural networks, etc. So, again I am pretty sure that in the very last week I have kept predominantly just as a closing week, which would be really interesting because it sort of connects through all the recent ideas about let us say ML or AI or data science or integration of all these three and application from a time series point of view. Okay. Thank you.